Dr. Garland wants to see us.
Oh yeah, I already have my little
You
meeting with him on
you
Monday.
met with him
On Monday.
on Monday.
Yes, sir.
Oh,
today?
you already met.
Yeah.
Great. Tomorrow I am planning to meet tomorrow.
Cool. Yeah. I figured out my qualifying results through Gamini. He like had him like, plastered. I'm like, oh well, I guess I know now.
Yeah, he talk about qualifying exam.
Yeah, I did better than I thought.
You had to take all the four or like,
I made a fail star on Thermo.
okay, I think I had the long one, classical.
Any pass?
No.
No pass? Start in thermal
Yeah,
and
that's it.
that's it.
Yeah. But if you're never taking a thermo course, I thought that was pretty amusing.
Yeah. We can prepare together for the next exam.
We will.
Hello.
Hello.
Hello. Ron.
How's your lab?
That's not good. We will trim the video.
Right.
He will trim your part that recorded in camera.
Yeah, no, it'll just disappear.
Yeah.
But I keep it forever. Just because it gets trimmed out doesn't mean it gets deleted.
Yeah. If you see waving his hand,
Yeah.
you immediately trim the video, trim the part and upload the remaining.
We'll just make a compilation of Rishi.
Yeah.
Like over.
And collect all the waves of Rishi in one video.
Top 10 waves.
Yeah. Huh? Is it written? Okay.
Yours. Now you both to move to back. Just remind we introduced Hamiltonian, right? And we construct Hamiltonian from the Legendre, Legendre transformation from the Lagrangian. That is definition of Hamiltonian or matrix representation. So here, matrix representation, this is a column matrix of the momentum, column matrix of the linear coefficient of this the linear in the Q dot, right? And then T is a projector. So both ways you can construct Hamiltonian. And today we are going to do some examples, see how to do that. Then once you have Hamiltonian, the equation of motion is these two. It's from the second order differential equation from the Lagrange equation reduced to the Hamilton equation. Then I write here is because what is L naught is first write down this Lagrangian, classify as second order or project term, linear term, and zeroth term. Now we also introduce matrix representation of the Lagrange, the Hamiltonian equation. We introduce the column matrix eta. So that eta is 2n by 1 column matrix. And then you can see the first half is the general coordinate, second half the conjugate momentum. Then this equation you should write in terms of like this. And here, this partial h partial eta is another quantum matrix representation. And then we also introduce the square matrix 2n by 2n square matrix G, which is defined by this. So this is a very simple way to express this equation of motion for the Hamiltonian. For the property of G, I don't remember, did I discuss the property of G last time? So G, if you can see where, if you take transport, right, so that is exchange, and that is negative of G. It's very easily you can find this. And then you can also find if the transport multiplier itself is this massive, it is equal to let's see, equal to unity operator. So therefore the G transport is nothing but equal to G inverse. Then you can also find G square is G multiplied its inverse, but it's minus. So the G square is G minus, so that is is equal to minus, sorry, that's minus. It's equal to minus unitary operator. So that is behavior of G, and later we are going to use this behavior in chapter 9. So here just introduce this square matrix. Now we are going to discuss today. First part, we are going to discuss this property of Hamiltonian. We know the Lagrangian, and we know how to find this separate coordinates of Lagrangian correspond to separate coordinates. There must be a corresponding conservation of conjugate momentum, right? So we look at from this behavior, can that also go to the Hamiltonian? So first, cyclic symmetry and its conservation. Those information how to analyze from this Hamiltonian. So now let's just try to remind in the Lagrangian formulation mechanism and the Hamiltonian. So you just compare those. Hamiltonian formulation mechanism. Okay. In Lagrange, if L is in Y, remember, under some of under some Q, what does mean? That means L does not include this one, right? So Qj minus 1, Qj plus 1, and Qn T, Qj dot, when I say, yes, Q1 dot, Qj dot, Qn dot, and T. So here, because if any environment this does not depend on this coordinate, right? So Q, let me see, so Qj is cyclic. How about in Hamiltonian? Let's see, Hamiltonian is summation of Pj, Qj dot, and L, Qj dot T, right? So here, if Qj, L, let me just write down. Q1, Qj plus minus 1, Qj plus 1, Qn, Q1 dot, Qj dot, Qn dot T. So if this is the case, that means the Hamiltonian is given by this, but here we do not have a Qj. And the first term is Pj, Qj dot, no Qj, right? So if this is a cyclic, that means Qj is also cyclic in the Hamiltonian. So that means the behavior of the invariance under the Qj kind of performance, if Lagrange does not change, then the Hamiltonian also. So if this Qj is a cyclic of an L Hamiltonian, it is the Lagrange is also the cyclic coordinate of Hamiltonian. Then we know the corresponding the conjugate moment Pj is partial L, partial Qj, right? Qj dot. That is constant, since we know that is, we remember this, right? That is from Lagrange equation. E dt partial L partial Qj dot equal to partial L partial Qj, right? And if this is 0, because there's no this term, so this one is not as Pj dot, right? So Pj dot equal to 0 and Pj is constant. So that is conserved. Conserved physical quantity. Then from here, if this is the case, how about in Hamiltonian? Okay, now here, since we do not have a Pj here, right? So from Lagrangian, if we know the Qj is cyclic, we imply that the conjugate momentum corresponds to Qj is constant, is conserved. How about in the Hamiltonian? In Hamiltonian, if Qj, so we know because from here, right? Equation of Hamilton equation, Pj dot is minus partial h partial Qj, right? Immediately from here, but h does not include Qj. That means Qj is a cyclic, so that is immediately got 0. Then that gives us Pj is constant. And then what you can see here, so Hamiltonian, we can rewrite, suppose this is alpha j. This is constant. So Hamiltonian is a function of q1, qj minus 1, qj plus 1, qn, and p1, pj minus 1, and then alpha j, which is equal to pj. Then the pj plus 1, pn, p. So you can see immediately from Hamiltonian, this is explicitly appeared in Hamiltonian, this conservation, right? If we have this cyclic, we immediately know, because Pj in Hamiltonian is one of the independent variable, we call the later we given name is canonical variables. So this variable immediately is constant. That explicitly here, just implicitly, is implicitly that from here, right? Implicitly give us this information about this conservation of conjugate momentum in the Lagrange, but in Hamiltonian, or in Hamiltonian formulation mechanism, that's direct give us this information. So that is one issue from here, and we know when we say the environment has a symmetry, right? So when we say the system has symmetry, that means under such corresponding this the operation, the system does not change. So that means system has a symmetry with respect to this coordinates, Qj general coordinates, and then that speaks cyclic, so corresponds to the conjugate momentum conserved. That both information in the Lagrange formulation mechanism and the Hamiltonian formulation are the same. So that's good. That means we didn't lose anything if we define or introduce Hamiltonian in this way. And we will find this more advantage than the Lagrange. Now, since this, so we can discuss if, for example, if Qj is translation, right? Translation displacement along J direction. So what that means that you need to know this conserve this linear momentum, right? It's a linear momentum along this direction is conserved. Or the system has a symmetry along under this displacement along a certain direction, then we immediately know there's a conservation. So that is conservation, general conservation. Okay, just want to remember in chapter 2 we discussed, right? General conservation theory. Is this. And if Qj is a rotation about an axis, some axis, I'm going to say J direction, then immediately we know this Pj equal to constant, which is, I'm going to just use Lj, okay, let's say Pj, which is Lj, which is angular momentum, right? Angular momentum. About J direction, right? The axis. So that theory is all transferred from Lagrangian to the Hamiltonian. Now the question, how about energy? Condition, what is condition of energy? Okay, just remind us in this Lagrangian formulation mechanism. We introduce energy function H, right? And H is also the product of this Pj out minus L. But H is a function of general coordinates, general velocity, t. That's still in the conclusion space. So when we introduce this and we know dH dt is equal to minus partial L partial t, right? Remember in chapter 2. So if the L does not depend on time explicitly, then H is constant. We have this. But H, remember, in general, H does not equal to energy. So we cannot say the system energy conserved. We just say the energy function is conserved if the Lagrangian does not depend on explicitly. Okay, we will not say that's the question here. So we need next step. So we need two steps. First, we go to see the Lagrangian does not depend on time or not explicitly. Then second, I'm going to see if, remember this, if this the coordinate does not depend on time explicitly, and the force is always kind of written in the negative gradient of the existing scalar potential. Then H equal to E. So if H is constant, so that gives us energy is conserved. So for the energy conservation, we need two conditions we need to judge. First, look at this Lagrangian does not depend on time or not. Then we look at these two conditions, right? Remember this. And similarly, let's look at the Hamiltonian. We also discussed Hamiltonian in general is not equal to, so now I guess, okay, here, got this. Hamiltonian formulation mechanism. Here. H is defined is this. And I think we already discussed also how to get the condition. Remember this? We discussed this, right? So similar as the energy function H, the condition, okay. And let's look this, okay, in this one, right? And let's look at total time derivative of Hamiltonian. If total time derivative of Hamiltonian like this, total time of H is 0, then we will have the Hamiltonian is a constant. So now let's see total time. So okay, this is a set. Whatever it is a function of Qj, Pj, and T, right? So that's Pj partial H partial Qj, Qj dot plus partial H partial Pj, Pj dot, and plus partial H partial T, right? Do this. Then we can just read, but you know this partial H partial Qj is negative Pj dot, right? According to Hamilton's equation motion, multiply Qj dot, and this one partial H partial Pj is Qj dot. Qj dot, Pj dot, and this two term cancel, right? So the total time derivative of Hamiltonian is equal to the partial time derivative of Hamiltonian. And remember, we already discussed or proved that this one is equal to the negative partial L partial T, right? Remember this? So, similar as like Lagrange formulation mechanism, if partial L or Lagrange does not depend time explicitly, the energy function is constant. Now here, if the Lagrange does not depend on time explicitly, H is also constant, right? Because dH dt is equal to partial H partial T, and the partial H partial T is negative partial L partial T, so that is. Okay, so this is the first, we looked at whether H is a constant or not. Then second, and so if this condition we already discussed before, I think last time, and the force is negative for gradient of the scalar potential, so we already proved that in that case, H equal to energy, right? Same thing like energy function. That is in this convolution space, this is in the phase space. Therefore, we have conclusion, okay, energy is conserved. So the conservation of energy, to answer this question, we need to judge two cases. First, look this, the Hamiltonian, whether it is dependent on time or not. That means the partial H partial time equal to 0 or not. Then if yes, Hamiltonian constant, but Hamiltonian equal to energy or not, we need to check these two conditions. Okay, so we discussed the symmetry, these cyclic coordinates, and correspond energy. Now, we also want to discuss another information is the property of Lagrangian and Hamiltonian. Let's just compare with see some similarity and difference. We have discussed some similarity in terms of symmetry and conservation. Now, first, L is defined T minus V, right, physically. So that because energy, kinetic energy is basically kinetic energy and potential energy. So that is include all the physical information here. We know that it is function, okay. Because it's so, okay. Let me see. It is a expression. Expression depends on the choice of general coordinates. Depends on how we select general coordinates, right? But its magnitude independent. Is independent on the choice of general coordinate. We have some of example in homework chapter 1, right? So now what that means, we have L, which is we select one side of general coordinates, and we have L prime is QJ prime, dot, and T. So their expressions is different. For example, we select the Cartesian coordinates and the spherical coordinates. We know the expression is different. However, the value is same, right? And also we know, because that is equal to, always equal to this physically, kinetic energy minus potential energy. The only difference is how to express kinetic energy and the potential energy in terms of different side of general coordinates. However, physically, it is just difference. So it will not change. That is this mean. This one is for first. Expression different, depend on selection, but this will always give the same value. So that is case. Now for the Hamiltonian, okay. For Hamiltonian, definition is, we know L does not depend on, I mean, if we consider this, the value, L does not depend on which side of general coordinate, but here, this one really depends, right? This is depend on the choice of this. Okay, since the first term dependent, so this one, the Hamiltonian, okay, its expression definitely change. Expression depends on the choice and its magnitude. Also depend. That means H okay, here, so this one is H is a function of QJ, PJ, P, and H prime is function of QJ prime, PJ prime, T. Then H does not depend on H prime. That is different. So we need to be careful in this case. Okay, I think that is the sum of implied information we need to keep in mind. Then now we are going to do some examples to see. Now, next step we are going to do some examples by either apply Lagrangian or use the Lagrangian formulation mechanism and the Hamiltonian formulation mechanism. We see the difference and we will see the solutions be the same, because whatever you use, the way is different but the final solution would describe motion assistance be safe, right? So now we are going to do some examples. Example 1. Example 1 is like this. Here we have a card. Okay, and we have a mass here. Contact one end contact with the spring, and spring other end is connect with the card. So the card move in the constant velocity. And we have a mass here. The card mass is 0. The card is massless. And C and card is 0. So now ask us to how to find this correct equation of motion of this mass, the particle here, and give the solution. So now how to do that? Find the equation of motion of particle and its solution. In Lagrange or Hamiltonian. Relation mechanism. So we will do both and see how to familiar with those. Then we are going to also make do some discussion. All right. So now first we need to set up this general coordinates, right? First, select QG. Okay. How to select QG? So now let's set up the coordinates. Since it's only move along this one dimension direction, right? So we just say this is along this. All right. So at any time, this distance is v naught t, right? The car move. And then if we say this is the distance of let me use here. Otherwise it would be here, so I'm going to use. So that is distance of x in the jet overlap coordinates that we looked at. So here that is x, then that is the position. Then they if I select that is x prime, which is relative motion to, because it's a spring, right? Also oscillate. So this oscillation is respect to the L naught, which is let me give a k. This is a constant of this the force constant of this spring. So which one we are going to select? We can either select this one or select this one. So now let's select this one, and we are going to select this, right? So let's first just x, since we only need one coordinate enough to describe the motion of that. So if we select x, okay, now first let's in this, I do not write this too much, right? I just say L. So that means in the Lagrange formulation for mechanism. So if we in, let's say in this one, then we first need to write the Lagrange, which is a function of x, x dot, and t, right? That is in general, since we have only one general coordinate. Now that be kinetic energy minus potential energy. So kinetic energy here, that is very easy, right? Potential energy, since this is on the horizontal, there's no, we do not consider the gravitational potential, right? They're all the same. So only the potential energy is from the spring. So that is minus half of k x prime, right? So x prime is, since I use x, not x prime, so that is x minus v naught t, right? That is potential. So you can see here, yes, it is function of x, x dot, and t. So when we write down the Hamiltonian, now we can solve it, right? So that is if I, okay, let's just say it. So now here, then we do this first we need to find this partial each term, then we are going to substitute into this Lagrange equation. Partial L partial x is this one, right? So that is k. I think we have the minus. I think it's minus. I think it's a minus thing. Right? There's a minus here. This minus here, we have two cancelled, and then x minus v naught t, right? That is the partial L partial and the partial L partial x dot is this term, m x dot. Then we put into here partial L partial x dot minus partial L partial x equal to 0. So that means we have m x double dot minus minus become plus, right? So that is plus k x minus v naught t equal to 0. So that is the equation that we answer the first question. Equation of motion, that is equation of motion. Now we're going to solve it. So this one is simple, right? If we define, define or use x prime equal to x minus v naught t, because this is just relative here. Then x dot prime equal to x dot, x double dot prime equal to x double dot, right? Because the v naught t is a constant. X, that's my mistake, is v naught, right? And x double dot prime is x double dot. Okay, then here I'm going to this became m x double prime double dot, the first term thing, and plus k x prime equal to 0, right? And then this one is simple, the harmonic, I mean, not like a harmonic oscillation, right? It's very simple. So then this gives us x prime. The solution is a cosine sinusoidal function omega t, where the omega, which means omega is square root of k over m. Right? If I divided this m, then this is x double dot prime plus omega square x prime, so that is this. Then immediately we can have x, because x has a relation with x prime is just x equal to x prime plus v naught t, right? So that is a cosine omega t plus v naught t. So we got solution. This is what we have used the Lagrange formulation equation mechanism. We select x as a general coordinates. So we get the solution. Now let's use the Hamiltonian formulation equation. Let's see, can we get the same thing and how to do that? Okay, before that we can also discuss here. We can discuss, since this is some physics. First, Px. Px is partial L, partial x dot, which is m x dot, right? It's not concerned because we know this Lagrangian has x. There's no separate, so because this, right? So immediately we got this. Second one. Okay, can you rewrite? So now let's rewrite L is Okay. L2 plus L0, right? You see here we have only this projector and zeroth order in terms of velocity. Because this. And so what does mean this? Immediately we know that is L equal to since potential has no linear term with the velocity, and also L2 is T2 is T. So immediately know the edge, or you just say either this way. This corresponds to what we discussed. This is correspond to these two conditions. So they are equivalent. If you remember, when this one equal to 0, the L1 disappeared, right? Remember, or T1, sorry, T1. This is a T, not T. So, and then the T equal T, second projector. So then that is when there's no L1, and L0 is only potential because it's term. So they are equivalent. Then you can see this one. Immediately, I will not, if you write down, okay. But you can prove yourself Px x dot minus L is equal to energy. That is very, you can prove yourself very easily. So now we know it is equal to this. Now 3. Does this energy function conserve or not? We're going to look. The Lagrangian does not depend on time explicitly. Yes. So because it's not equal to 0, so dh dt is not equal to 0, so h is not constant. And that means also energy is not constant, since h equal to energy. Right, so we discuss. So that means when we have this the result, we can analyze what kind of motion. So this is an example. Now we go to in Hamiltonian formulation of make this, how to do that. We should do the same conclusion, but now let's see. In this case, we need first construct Hamiltonian, right? To construct Hamiltonian, we learn there are two ways. One is just follow step 1, step 2 until step 5, one by one. Another is matrix representation. So let's do twice. Each individual will also do that, since I want to you also familiar with this. Okay, because h, let's first, is Px x dot minus L, right? It's because we only have one general coordinate. And then here, let's substitute Px x dot minus L is half of m x dot square minus plus, right? Plus half of k x minus v naught t square. So now, then this is if we use step 1, so this is the first step. And then second one, we're going to replace x dot by Px, right? So because Px here, right, equal to m x dot. So x dot is Px over m. Therefore, the Hamiltonian we can immediately write down here, since this is step 1, step 2, step 3, right, inverse. We already did. So now h is Px over m, that is x dot, minus here half of m Px over m square plus half of k x minus v naught t. And then here, this is just half, right? So then we have a half m over Px squared plus half of k x minus v naught t squared. Immediately, no, this is energy. Let me leave here. We are going to discuss this. So I just now, this is the first way we can construct Hamiltonian. Then we can also alternatively, Hamiltonian is half of this matrix. We're going to use this. if you prefer use matrix. So either way, you prefer this way actually, if it's very simple, very easily you can do. In this case, let's first, what is A? A is here, right? Okay. Let's go to here. You see here, did I write on before? Yeah, oh, already here, right? So Lagrange only has a quadratic term and the zeroth order term. So A, right, 0. No the linear term, so no coefficient for linear term. Then how about T? T here. Please dump onto a half of QG. Right? Remember we have this formula. So you can immediately got the T is, because it's one dimension, so this matrix is just numbers, right? So T inverse is 1 over n. So Hamiltonian half of P, because P now is one dimension, only Px minus 0. And then 1 over n, this T inverse Px minus 0. What is L naught? L naught is this negative, this term, right? That's L naught, this one. So negative half of Kx minus L naught P. Then you can immediately got this, that is a P x squared over 2m plus half of K x v naught T squared. And you can see here, I didn't write on the edge here, but you will see there like this. Okay, so we first construct Hamiltonian. Then we are going to find equation of motion by the Hamilton equation. So now next one. X dot is partial h partial px. Px dot is negative partial h partial x, right? So then let's do that. X dot, okay, partial h partial px is a 2-2 factor, so that is px over n, right? And this one is partial x. Here we have 2 cancel. We have negative k x minus v naught t. Then next step, here I have this, right? So x double dot is p x dot over m. Then p dot dot px dot is this one, so I'm going to substitute here. Then you will have this is minus k x minus v naught t. You see same as here. You can move to the left hand side, right? So you can see the solution. If we use this one, come to here, do the same thing. So you have finally solution is same thing. P plus v naught t. Same solution. That means whatever you use Lagrangian or use Hamiltonian, this will give the same, right? Yes, the answer is the same. Then now, once we have to resolve, we can also discussion. So here we also look here. I just use this one. Now px. We are going to look whether it is conserved or not, right? Because px dot is partial h, partial x, negative partial h, partial x, right? Is here. Is equal to k over x minus v naught t. It's not equal to 0. So the px is not constant. And that's because here Hamiltonian, you will see here Hamiltonian, we have x, so x is not cyclic. So that is the same thing here. And the second one, actually same thing. I can use the same thing here. Because here, so because this condition either for both for energy function and also for Hamiltonian, right? So we have immediately have Hamiltonian is equal to energy. That is same thing here. Then the number 3. So here, this one depends on time explicitly. So we'll have partial h, partial t does not equal to 0. That means dh, dt does not equal to 0. Then we have that the h is not constant, not conserved, and of course energy also, since h equal to energy. So you can see the conclusion safe, right? We discussed. All are safe. All right, so this is we first use the general coordinate listed like x. Then we use either Lagrangian combination mechanism or Hamiltonian combination mechanism. We get the same result, and that makes sense. So now, let's consider we use the x prime as general coordinate. How about this case? In this case, we are also see the Lagrangian and L prime, L they do not equal to each other, but they will give us the same result. And H and H prime you will see is also different, so we are going to see this properties. That is now the second one. We are going to select X QG as X prime, only X prime. Okay, just X prime. Okay, in this case, now, again, first in the Lagrangian combination of magnets, we have, that's in this case. So, Lagrangian, let's fill L, let's first, since L must be equal to L prime, right, is half of mx dot square minus half kx minus v naught t square. And then we are going to substitute x dot is remember is x prime dot plus v naught t square. Since we have x prime equal to x minus v naught t, right? Then the x is equal to x prime plus v naught t. Then we do the x dot is v naught minus t. V naught x dot. So that is the replace, and here minus half k x prime square. This is our L prime, right? So L prime is x prime dot, and t. Okay. Then now we're going to solve. That's why they are equal, you see here, right? Even though this expression is L prime, and this expression is L, you see that they are different. The difference is this term and this term. Different, but they are equal, since they all define this difference of kinetic agent. X prime is half minus half kx prime. And partial L prime, partial x prime dot is here we have half at m x prime dot plus v naught. Then the Lagrange equations of D, we also prove that even when changing another set of general coordinates, the Lagrange equation is invariant, right? So it's still keep the same. That we prove. So let's do that. We have d dt, L prime, this one is m x dot prime plus v naught, and minus we can plus k x prime equal to 0. So here, that is mx double dot prime, right? A naught is constant. Plus kx prime equal to 0. So the solution, x prime is a cosine of t. Same thing, though we got to divide here. And x is a cosine of t plus a naught t. Yes, you see the solution the same. Even though we change its coordinates, it will not affect the final result. So here we have this result. Now we can also go to the discussion. Here, follow the same thing now. Let's discuss one by one in this case. Okay, here. Px prime is partial L partial x prime dot, right? That is equal to m x dot prime plus v naught, and which is not constant, since we know x is dependent on time, x dot also dependent on time. That is because x prime is not separate, right? As we can see, x prime from here is not separate. So that is again, we have this conclusion. Then second one, L prime here, we need to rewrite L prime. So L prime is here. That if it extends, you have a half of m x dot prime square plus x dot prime v naught plus v naught square minus half of a kx prime square. Here you have this linear term. So this exists, right? Then h immediately h I think I can just if you write you want h prime here, right? So you see the h prime will change. It's px prime x prime dot minus L prime, and I give you a result. It's very simple. That is m is half mx double x dot prime square plus half of kx prime square minus there's additional term. So this one, if in term of x prime is kind of energy, t prime, if you say this one in term of x prime is potential energy, but here we have a diffusion term. Even though you use prime as energy, it is not, since here also. Since here, L1 prime is not 0, right? So that case. Then the number 3, partial L prime partial t is 0, right? Since no, we do not have a time dependent time explicitly. In this case, if we change the new general coordinates, the L depend on time explicitly, but if we replace x by x prime, we do not have this, where x prime? Yeah, either here or here, right? So dh prime dt is b0, h prime is constant. You can see here, h does not, h is not conserved. If we select x as a general coordinate, the energy function does not depend on, conserve. But if we replace x by x prime, the new energy function at h prime is constant, is conserved. But since we know, because harmonic, h is not, h prime does not equal to a, right? So you see here the h is energy function. It is indeed depend on the choice of the general coordinates, but Lagrange not. Now let's do the same thing for the Hamilton formulation equation. And you will see this, okay, so H prime by definition is Px prime x prime dot minus L prime, right? That is definition. Then we substitute this Px prime x prime dot minus L prime is here. L prime is half of m x prime dot plus 3 naught square minus, this is plus half of kx prime square, right? Then we are going to px prime is equal to m x dot prime plus 3 naught. So that gives x prime dot prime is px prime over m minus 3 naught, right? Then we substitute this into this, so x prime is px prime divided by m minus 3 naught, and minus half of m inside is px prime over m minus 3 naught plus 3 naught squared plus half of kx prime squared. Then you organize, you will see here we have this term, so we have a half. But here we have a cross product px prime is v naught. Then we do not have that one. Let me put it down. Okay, then we'll give you final. I think that this final is very simple, so I think you can do it yourself. Minus v naught square plus half of kx prime square minus half of m v naught square. Okay, that's different. Okay, so that is this case. Now we have the Hamiltonian. Or alternatively, you can use H prime is half of P prime minus A prime, P prime inverse and P prime minus A prime minus A naught prime, right? And here again we do not, we have A, yes. We have L1 in the L prime, right? So we can see here, this is L prime, half M, this one. So here A prime is here. I think I have a half factor half. Okay. I think I missed this factor 2, right? Yes. So that is this. So A prime is M V naught, right? X prime dot, so we have half after the M V naught. And then the T prime is still M. In the projector, this one, right? This is the projector. So this one is still here. So H prime is half of Px prime minus M V naught, that is A prime, and 1 over M Px prime minus M V naught, and minus V naught. Here, this, sorry, minus L naught prime. So L naught prime is this one. So that is minus half of Kx prime squared. Then finally we have 1 over 2m Px prime minus M V naught squared. Okay, now this one. We have also another one. You see, this is also zeroth order, so we have minus half of M V naught squared. this one plus half of k x transfer and minus half of n k transfer. Okay, so you can see, are they same? Yeah, I use different way, but they are same. So that is depend on your choice. Okay, once we have this, now we can have this solve this equation motion. X prime dot is partial x h prime with respect to p x prime, which is this term. 2 cancel, so we have m p x prime minus m p half prime. And px prime dot is negative partial h prime partial x prime. It's only this term, that is negative k x prime. Okay, so in this two, what you need to just do this term divided again. So x prime double dot is equal to m px dot, and then you do this substitute. So the solution, same. Just give you the solution. It's very simple and the same. We have solution is m x double dot prime plus k x prime equal to 0. So we have x prime is a cosine omega t, and x is a cosine omega t plus a naught t. Yes, actually the same. Then the discussion, okay. Discussion. First, definitely they are not equal, right? You can see here this is h prime, and the h, if you remember h, we have h is h is half of a p. Remember that h is px squared over 2n plus half of a k x minus a naught t squared. Right? So the h prime is this one. So they are not equal. Yes. So that means it depends on the choice of that gives us this, but L equal to L prime, right? That is different. Second one, again, let's look at this px prime. Px prime because px dot prime, the equation, Hamilton's equation of motion, px prime dot is equal to, here, right? Minus kx prime not equal to 0. So we have px prime is not equal to constant, not conserved. Again, because x prime is not separate in x prime. Number 3. Because we have L1 does not equal to 0, so immediately not h prime does not equal to 0. You can put yourself. And then number 4, partial L prime partial t equal to negative partial h prime partial t equal to 0. So that's dh prime dt equal to 0. And h prime is constantly conserved. However, it does not equal to anything. So even though we change the new or another set of general coordinates, we have different expression of Hamiltonian, different value, different behavior. In the old one, Hamiltonian does not is not conserved, but here in the another general coordinate Hamiltonian, h prime is conserved, but it's not equal to energy. In the first one, energy equal to the Hamiltonian, but not conserved. So you be careful when you select the general coordinate for this when we deal with the Hamiltonian. We have a time, so I think we can also go to another example. If not finished, I think we can finish on Thursday. All right, so now let's do another example. Just let you have more experience to deal with the system when we apply the Hamiltonian and the Hamilton formulation of magazine. This case is we have, let's say, we have two mass connect with the spring here. So let's say the mass are same. Okay, M1, M2. Now we have a central mass here, which has a uniform velocity t moved along this direction. That is situation. This is like a dumbbell of two mass. So here this spring constant k, right? If, right, is the central mass, it moves uniform along this direction. So now find let's see, this solve it. Yes.
Do they oscillate while moving or like just?
Yes, they are moving and oscillate like this.
Oh.
Yeah, central mass move, but they are also, because the spring, so they also vibrate correspond to the central mass. Okay, that is the situation. Let me see. We can ask the question, the final, yes, solution. Right. Okay. Equation of motion. Solution. Okay, so that is question. Now we are going to first, in this case, let me see, just use the Hamiltonian. We can, since we make a comparison in first example, so now the next one, we just apply the Hamiltonian sequential motion. Okay, let's do this. So because it's along the one dimension, right? Now we are going to set up the coordinate. See, this is in this direction, and then assume that here we have okay. X1, X2, okay, so now X1, that is the position of the first one, right? This is X2, and then we have relative to central mass, I'm going to say X11, X21, here. Then we are going to define the difference between these two is X. That is, okay, so that's a defined this. So now let's first define the relation here. Center of mass, we know by definition, right, is M1, X1 plus M2, X2 divided by the total mass, right? That is center mass. And the relative position is X2 minus X1. X2 minus, so that is X, right? That is defined. And we are going to use this 2 as our general coordinate. Okay, so now we are going to select X center of mass and X. Because we know the motion is easier to separate the center of mass motion and the relative motion, since we know center of mass keep the constant motion. Okay. Do the same thing as to save time. I think we already discussed how to convert this X1, X2. Let me just do that here. As I said, kinetic energy, there are two ways. Just set all, sum of each individual kinetic energy together, right? Either this way, or T center of mass plus T relative, right? There are two ways. So if you use this way, you need to find what is x1 in terms of xc and cm and x and x2. If you remember that in chapter 1, we already discussed, I give you this x1 prime. Okay, so now I give you x1 prime is minus xcm, center of mass minus x1, and x2 prime is relative center, right? So that is x2 minus xcm. This just remind you in chapter 1, so I give you the formula here. Minus m2, m1 plus m2x equal to m1 plus m2x. So with this, then you do the x product. So here, that is half of m1 plus m2 xcm tau squared, right? The first one, center of mass. The second one, the t relative, is, let me write down first, then I can write the whole, is half of m1 x1 dot prime plus half of m2 x2 prime dot, right? That is two kinetic relative to the center of mass. So that is the t prime, right? Center of mass, total mass, is the center of mass is the velocity, and the relative kinetic energy is two particles relative to the center of mass, that is x1 prime and x2 prime. Then if you remember, I substitute the x prime here, so you will find that equal to, the first term still keeps same, x center of mass dot square plus half of mu x dot square. Here, mu is reduced mass. Remember, chapter 1 we discussed. Right. So this is first they write down the kinetic energy. Once kinetic energy write down, the potential energy is easier, right? Okay, let me write down finish potential so we can stop here. Then the Lagrangian is a function of x, xcm, x dot, xcm dot t, right? That be kinetic energy minus potential energy. Kinetic energy we already write down here, half of kinetic energy for the center of mass plus reduced mass and dot square and potential. So the potential is only the relative, since this move around the horizontal, we ignore this gravitational potential, only this the potential of spin. And that is half of k x squared, right? X means is the x minus L, sorry. X minus L, if we select the L as the initial length, or x minus x naught, right, the relative length. Okay, I think if we write down here, the next step to write down the Hamiltonian is easier. We stop here and we can finish on Thursday. So, actually, if you want to do yourself, you can do. That'd be nice. now?
Yeah.
How about this?
I
You're
think
fine?
Yes.
Okay. I know there's another class, so I don't want to leave it.
Yeah.
Tomorrow. Okay.
Thank you.
Okay.
Jacob.
Namaste is Nepali, right?
Yeah.
Ah, Indian.
Both. Both.
You guys also say Namaste?
Yeah. Namaste is very popular and very admirable in Nepal.
What is that? I mean, is there meaning?
Like hello.
Okay, we say
Greeting.
Ayubowan.
Greeting. Namaste. It's our culture.
How did Anil say it? I don't care about you, but I respect the good in you.
Namaste को meaning पूजा दाइ अनिलले सिकाइदिएको
I was like, oh, okay.
यसको नाम के हो यसको नाम के हो
It's wrong to correct.
हेलो
I can understand some
Good.
stuff, but
तिम्रो नाम ईश्वरङ्गा हो
How different is the language?
Mera naam Suratpur.
yeah you also
Not
understand
Mera.
Is it?
Mero.
Meru. Okay.
How different is the language from?
If you said Mera naam,
Yeah,
it's
single is
Indian.
totally different.
Oh, okay.
It's like
लेसको
like
मुट्ना
moon and the earth.
Okay, okay.
But the thing is, usually Sri Lankan people watch Indian movies and also I'm kind of used to the language.
Different language.
Okay.
Different
Yeah.
language?
We speak Nepali.
I can't do it like any better, but there are people who can speak really like singing.
Nibal.
Many things like
I'm just always curious about
you know
like,
Hindi.
Hindi, yeah.
just how,
You speak
Nibal.
Hindi.
No,
how
no.
much cultures and
Yes,
languages
yes,
like
yes.
My
vary
brother,
when they're so kind of.
he now
close,
some work.
Some
It's really,
Yeah,
it's
because
really
in company.
But like
Yeah.
my roommate is from Kerala, yeah.
Indian and Nepalese
Oh, yeah.
are
I saw him. I
not the
was-
same,
Yeah, go, you
but
make it, right?
the
Yeah.
words
So,
are
He is
very
speaking
common.
a different language.
Yeah, yeah. There are very common words, common phrases.
Malayalam or something.
in Hindi and
Okay,
Nepali.
this language is different, but thing is
Near,
like
India?
food and everything.
Yeah.
Like is similar to
And
us.
Bangladesh.
Oh, okay.
Now, India is Nepal is surrounded by from 3 sides of India and 1 side with China.
No, see.
No sea.
Okay,
land